Why did supermassive black holes form just after the birth of the universe? This question puzzled astronomers for a very long time, and now we have got a theory explaining an answer to this question. The universe was very different from what it is today in its first few 100 million years. At that time, gravity was just kicking in to clump together clouds of dust and dark matter, and the first generation of stars only rich in hydrogen and helium were beginning to form. This is what you and everybody previously thought, yeah? But surprisingly, some giant black holes have a mass of up to 1 billion solar masses had somehow formed. If we consider the traditional picture of black hole formation and growth, the extremely young universe, less than 1 billion years old, had surely not existed long enough to allow black holes to bulk up to 1 billion solar masses in the usual way. And if our current black hole models are accurate, such massive black holes, or quasars in particular, should not have formed in that era of the universe. But in reality, they did exist in the early universe. Can you figure out how such massive black holes formed in the baby universe? How did they gain so much mass in just a few million years? This changes our current understanding of black holes dramatically. So let's begin the video. Do you know what a quasar is? No worries if you don't know, I am here to tell you. Quasar is an abbreviation which stands for quasi-stellar radio source. It is an active galactic core or center, which is a rapidly spinning supermassive black hole that feeds on gas at the center of a distant galaxy. Quasars are among the brightest sources and the most powerful objects in the universe. Some quasars have luminosities even thousands of times greater than our own Milky Way galaxy. But the fascinating question is, what makes these objects so powerful? The answer is their environment. Yes, but how? Quasars usually reside in galaxies that are home to enormous gas supplies. In such a plentiful environment, as the gas spins around the black hole while falling into it, it gets heated up in the process. Hence, it emits radiation across the entire electromagnetic spectrum. As the supermassive black holes in nearby galaxies do not have such huge quantities of gas, quasars are typically found in distant galaxies. Even the nearest quasar, Markarian 231, lies about 600 million light years away from us. So how do such majestic spinning structures form? Presently, two evaluated theories can explain the formation of black holes generally. As per the first and the widely known theory, when a massive star dies, it can leave behind a black hole that can be up to around 100 times the mass of the Sun. Over time, this black hole can consume the surrounding material. It makes the black hole grow bigger and bigger until it becomes a supermassive black hole, millions to billions of times of the mass of the Sun. But the main issue here is that the scientists state that no black hole can consume enough material in just 500 million years to attain the mass of 1 billion times of the Sun. That's because as matter begins to gather around a black hole, it settles into an accretion disk. The material in this disk travels around the black hole at speeds comparable to the speed of light. Due to this motion, the disk gets heated up and blasts out jets of radiation across a broad spectrum of wavelengths. The intense pressure exerted by this radiation pushes away nearby matter, limiting how fast black hole can swallow additional mass. This theoretical maximum accretion rate of a black hole is known as the Eddington mass limit. And even if a black hole can pull in matter faster than the specified limit, the enhanced accretion is expected to produce powerful winds. These winds will further drive the surrounding material away, thus halting the growth. All these factors limit how fast a black hole can grow. So if this framework is accurate, it refutes the theory that quasars formed in the early universe in the usual way. This brings us to the other possible quasar formation theory. According to this one, some stars of short lifetime, possibly having an existence of nearly 250,000 years, collapsed to form black holes that carried mass up to 100,000 times the mass of the Sun. In this case, as the newborn black hole was quite massive, it could have quickly accreted mass equivalent to billions of solar masses. They also estimate that a quasar must lie somewhere between 10,000 to 100,000 solar masses at its birth, which further sustains this theory. But for such a black hole to form, the parent star has to be extremely massive, almost tens of thousands of times more massive than our own sun. But we have never observed such gigantic stars in the known universe. Even the most massive star discovered so far is just about 300 times the sun's mass. Furthermore, we don't know any current mechanism that can drive the formation of stars thousands of times of sun's mass. However, we know that the conditions in the early universe differed from what we see today. So as per simulations, such stars could have formed in the early universe. Although the phenomenon would have been very rare, it is possible that massive stars formed at the junctions of powerful streams of dense and turbulent cold gas. But this would have required some truly exotic conditions, such as backgrounds of intense ultraviolet radiation or supersonic flows between gas and dark matter for stars to form. And unfortunately, none of these exotic conditions resembles the environment in which these early quasars have been formed. So how do we explain the quasar formation? To answer this question, scientists ran simulations of the gas streams. Usually, a baby star forms when a dense knot of material in a cold cloud collapses under its gravity. But in considerable turbulence, conditions are not stable enough for such a collapse. So in the simulations, the turbulence generated by the intersecting streams prevented the formation of average stars, the ones which we see today. Instead, this made the cloud in the simulation grow so massive that it catastrophically collapsed into two giant stars, almost 31,000 and 40,000 times the mass of the sun. And if the gas from the streams continues to feed the clouds, a supermassive black hole, billions of times of the mass of the sun, can form and grow in just a few hundred million years. This explains how supermassive black holes could have formed at the intersections of gas streams even without exotic conditions. Roughly 200 quasars formed within the first billion years of our universe's history. And now we probably know how. Drop your thoughts and ideas below in the comment section. If you enjoyed the video, hit the like button and subscribe plus ring the bell for more videos. And until next time, thanks for watching.